see the property of principle of work done and change of kinetic energy. Okay. Famous pendulum. Okay. I have pendulum. Okay. I release this one over here, 45 angle, measured from this position, and I release it. And then I want to estimate the velocity at this position. Okay? And also I want to know the tension at this position. Okay? That's my interest. What we can do. Okay? Here is a pendulum. Say this is a theta. And I want to know the velocity of this pendulum when this pendulum passes theta equal pi over 2 or 90 degrees. Oh, then it means that from this stage 1 to stage 2, okay, the problem asked us to find out the velocity at stage 2. Okay, what I can do. Because it involves velocity, not acceleration, so I don't have to use the Newton's second law. I may choose principle of work done has to be equal to kinetic energy. Let's use that concept to get the velocity of pendulum at this point. Okay, work done from 1 to 2 has to be equal to summation of all worked done on this element, right? And how to apply it. Then it means to apply that concept, what would be the first step we have to follow? Okay, so we have to find out all the forces and the displacement. So first step, find out all the forces acting on the particle of interest. Okay? Now, can I answer? How do you find out all the forces acting on the particle of interest? Huh? Yes, free body diagram. Okay? So, free body diagram. So let's draw the free body diagram of this particle. How to draw the free body diagram? Anybody remember how to draw free body diagram? Kim Sun-min? How to draw free body diagram? What does it mean by free? Free from what? Okay, let me ask you, Kim Hyun-woo, what do you mean by free? Free from connection or free from any constraint. So I am free this body of interest from the connection of pendulum. So I see now there is a force acting on this direction, and I denote that is tension. And in this course, there's two kinds of course. And one is the force due to the connection or constraint. And what other force? Field, the force due to the presence of gravitational force field or electromagnetic force field, so on, so on. So that is mg. Okay, I did second step. Now I can write work done as the following form. Okay, work done U12 is equal to, from this observation, I can write one is mg. Okay, what is the displacement of mg force? From here to there, right? Okay, so I can say, okay, that is y1 minus y2. That means I am using coordinate, y coordinate, and I denote that is y1 and that is y2. Okay. And other force, that is T, multiplied by some distance or displacement from 1 to 2, and I denote this is S and a T. And what is it? T multiplied by ds. The projected force on S coordinate is 0 because that is tension acting on this particle. Therefore, this is 0. Now I have work done is simply mg. If I use this distance is h as before, that is mgh. Okay, what I did is I just calculated the work done, which is induced, which is force dot product displacement vector. I operated that one. I did not apply anything that has to do with the work done will induce change of kinetic energy. I did not use that. Often you mixed up the concept of change of kinetic energy as well as work done, right? So I emphasize I recommend you use this approach. You write down work done is change, it has to be force dot product dr force, and then, okay, this is step 1. And step 2, you write down work done induced change of kinetic energy. Okay. Then you write down over here, and work done is equal to change of kinetic energy. What is it? T1 minus T2 or T2 minus T1? Okay, T2 minus T1. That is 1/2 m v2 square. Therefore, from this equation and that equation, from these two equations, we obtain what? mg h is equal to 1/2 m v2 square. So I got v2 square using principle of work done and kinetic energy. Okay, what is the tension at this state 2? T2 is equal to what? Okay, to find the force, I have to draw free body diagram. Okay, and I draw, okay, here there must be tension, which I call T2, that has to be equal to what? The force induced mass times acceleration, okay? There is some acceleration, that MAT tangential component, okay? And there is another acceleration, MAN, that is normal component. And we do know that AN, if I use this coordinate, that is AN is V square over rho. Here rho is the length of a pendulum. So I obtain from this graphical expression of Newton's second law, I obtain T2 is equal to M V2 square over L. Right? So that is a systematic object. Then what is the tangential acceleration at state 2, AT? Oh, yes, yes. I omitted mg over here, right? Right, so you are alive. So correction has to be T2 minus mg has to be equal to m V2 square divided by L. Is it correct? What about if somebody say this MAN has looked downward? What is the sign convention of AT and AN? Okay, remember when we get the concept of tangential acceleration, okay, this is unit vector in tangential direction, okay, and we assume that this is moving that way, then this is ET prime, then what we have is this, therefore this is what is related with normal direction. So the normal direction and the tangential direction has this rule. That is important. Okay? Whenever you are confused with the direction of acceleration, you come back to the basic relation or basic derivation. That's why basic derivation is so important. Understand? Good. Now, let's go back another example.